But why this time slowdown, and what does it even mean? Some of you may have heard of some of the consequences of special relativity. Today, you and I are going to understand where these, sometimes perhaps rather counterintuitive, things actually come from. Two established facts by the beginning of the 20th century were the following. First, all inertial observers are equivalent, where inertia means that the observer is moving at a constant velocity, and second, that the speed of light is constant. In this video, we are going to see the consequences that come from these assumptions. We will first understand why time cannot be absolute, after which we will see how time dilation and length contraction, probably the two most famous aspects of special relativity, arise from our assumptions. That will be the first video. The next video will then build upon the results of this video to derive the Lorentz transformation, how the concept of simultaneity is frame dependent, and lastly, we will understand the invariant interval, which is also closely related to the Minkowski metric. For the start, we're simply going to put ourselves into a coordinate system that is denoted by the letter A. In this coordinate system, we are observing an object, the white little sphere, that will start moving along the x-axis of the coordinate system. That could, for instance, represent a train moving at a constant velocity or whatever. We also see another observer who is sitting in a coordinate system denoted by the letter B, that is also moving along the x-axis, just a little bit slower. From the point of view of system A, that scene looks like this, with the white sphere moving a little bit faster than the coordinate system B. Now, we can look at the same events again, however this time we will take the point of view of an observer in system B. From this point of view, the object is moving significantly slower and system A moves to the right. This should make sense because system B is following the object, so the object should move more slowly when looked at from system B itself. Now, what if this moving object was a photon, which is traveling at the speed of light along the x-axis? Again, we add a second coordinate system that will also move along the x-axis with a velocity that is slower than the speed of light, and which in fact has to be slower than the speed of light. According to the second axiom that we discussed earlier, which states that the speed of light is the same in all frames of reference, the movement of the photon has to look exactly the same in the coordinate system B. So again, the photon is traveling along the x-axis with the same speed as before, the speed of light, while now the system A moves to the right. Let's try to make more sense of that by again looking at this scene from the perspective of system A. To actually measure the speed of light, we will put another observer into system A, who is positioned 5 light seconds away from the origin, where 1 light second is the distance traveled by light in 1 second. With this measurement, we're going to try to make sense of how both system A and system B could measure the same speed of light. At time t equals 0, the photon starts moving and also system B starts moving along the x-axis. We are going to freeze the scene once the second observer in A detects the photon. In system A, the photon traveled this distance, which is 5 light seconds. In system B, however, the photon traveled a shorter distance. If we assume that the clocks in both systems run the same, which seems like a decent assumption according to our everyday experience, we conclude that observer B measures the speed of light that is smaller than the speed of light in system A. So something apparently went wrong because the two observers do not measure the same speed of light. We essentially just saw that the two assumptions, the speed of light is constant and time is universal, are in fact not compatible. Therefore, as there is some pretty strong empirical evidence that the speed of light is constant, we have to let go of our traditional understanding of space and time. Instead, we are going to have to accept that the clocks in both systems do not necessarily run the same. Time is not absolute. Next, we're going to answer the question by how much exactly the clocks in both systems differ, which will bring us to time dilation. Now, as the speed of light is the only thing that all observers can agree on, we better use the speed of light to actually define what a second is. In order to do that, we're going to take two mirrors and put them some distance apart from each other. If you somehow manage to put them this far away from each other, then the time it takes a photon to get from one mirror to the other is going to be equal to precisely 1 second. So we're going to define one unit of time as the time it takes light to get from one mirror to the other. By counting the number of times the photon bounces back and forth between the two sides, an observer can deduce the time that has passed in his coordinate system. Again, we will add a second observer in the coordinate system B and also give her a light watch. The coordinate system B is again going to move with respect to A, but as the speed of light is constant, observer B is going to have a very similar experience when looking at her light watch. The photon simply bounces back and forth between the two mirrors. Now, something really interesting happens when observer A looks at the light watch of observer B, because now, from the point of view of observer A, the photon that is bouncing back and forth in the light watch of observer B has to travel a longer distance. As the speed of light is constant, light watch B has to tick more slowly than light watch A when observed from system A. And observer A also knows that observer B considers one tick of her light watch as 1 second. So when, for example, 3 seconds passed for B, more time has elapsed on the light watch of observer A. So moving clocks run slower. Now, we kept talking about observers. Let's pause for a second to think about the question, what actually is that? What do we mean by observer A and observer B? Intuitively, you might be thinking that it is one person located perhaps at the origin of the coordinate system, surveying everything around him, or that he is located at the position of the camera that is used in the animation. But actually, an observer is something a bit more abstract than that. To see why, let's just look at this scene again. An observer positioned at the camera would not actually be able to see any of the photons in this scene that are bouncing back and forth between the two mirrors, because those photons never actually reach his eye. So instead, an observer is more something of a big brother figure, a sea of individual observers with clocks that record every event that takes place. Now, in this scene, for example, you can see a handful of those infinitely many observers, represented by the letter A, that are at a fixed position in system A, so they record all events from the point of view of system A. Where, to clear that up as well, an event is something happening at a certain location at a certain time. So an event is described by 3 spatial coordinates and 1 time coordinate. Whenever an observer detects a photon, he notes down his position and his time to be studied at some point in the future. So, moving clocks run slower. But by how much exactly? To answer that, we're going to look at the light watch of B again in more detail, such that we can determine the difference between the 2 light clocks in the 2 coordinate systems. We will keep track of the trajectory that the photon in the light watch of coordinate system B follows from the point of view of system A. And now we can use that to do a little calculation. What we want to know is the time it takes the light to traverse this distance, as seen from system A. Once we figure that out, we can compare it to the time it takes the photon to go to the other side of the mirror in system B. This distance here is simply the separation between the 2 mirrors of the light watch, which in the animation is set to 1 light second. So, an observer in B will assert that it took the photon 1 second to go between the mirrors. Because, if you remember, in system B, the photon just goes up and down in a straight line. In system A, however, the photon has to travel this additional distance, which is the distance the light watch B moves in between 2 ticks. The length of the distance we are interested in can then easily be calculated using the Pythagorean theorem. So, the time between 2 ticks in system A is then given by the length of that hypotenuse divided by the speed of light c. You can solve this expression yourself for the time delta t, which is again the time between 2 ticks of light watch B as seen from system A. What you will get is the following. The prefactor, which reads 1 over the square root of 1 minus v over c squared, occurs quite often in special relativity and is called the relativistic gamma factor. If you plug in some values for the velocity v, you'll see that this gamma factor is always greater than 1. So in system A, we get this lovely expression for the time that elapses on a watch of system A between 2 ticks of a light watch B that is moving. In system B, the calculation is a bit more straightforward. The photon only has to traverse the distance between the 2 mirrors between 2 ticks. Therefore, the time between 2 ticks can easily be calculated to be the distance d over the speed of light, c. When comparing the two expressions, we see that the time interval in system A is scaled by the gamma factor. That is called time dilation. To recap one more time what we just discussed, when you compare your watch with a watch that is moving relative to you, you would argue that the moving watch runs more slowly. For example, every time the light watch in B ticks, we know that 1 more second has passed for an observer in system B. However, we in system A notice that every time the light watch in B ticks, more than 1 second has passed on our watch, something like 1.5 seconds if observer B is moving at 75% the speed of light. To clear up some more points of potential confusion, all inertial frames are equal. So an observer in B would, using exactly the same arguments as before, argue that the light watch in A is moving more slowly. So it's just that every watch that is moving relative to you appears to be running more slowly than your own watch. So none of the observers is actually aging more quickly than the other. Things like the twin paradox, where one of the twins flies around the sun at 90% the speed of light and comes back younger than his twin brother, are only possible because one of the frames is actually not inertial. The twin brother flying around the sun has to, at some point, accelerate. So he is not actually inertial and he will indeed return younger than his twin brother. Next, we will see that the notion of length and distance is in fact also a frame-dependent concept. We will try to determine the length of this arrow that is at rest in system A. Now, the observer in A is going to determine that length in perhaps a slightly unconventional way. The only thing that we've really understood so far are light watches, and that the speed of light is the same in all frames of reference. So we better somehow make use of that to also determine this distance. Let's first look at this measurement from system A. We're going to put another observer B at one end of the arrow and move that observer along the arrow with a velocity v until it reaches the other side. And we use the light watch in system A to measure the time that elapses until B reaches the other side. Using the simple formula distance equals velocity multiplied by time, we can deduce the length of this object. We saw that the watch in system A ticked roughly 8 times, which observer A can then use to calculate the length. Now, what does this look like in system B? Observer B sees the arrow passing by, also with velocity v. So she can also deduce the length of the arrow by measuring the time it takes the arrow to get past her, and then using the same formula as before. Note that we're using different indices here for L and T because they are frame dependent. The absolute relative velocity v, however, between the two systems A and B is the same. Doing that measurement, we see that the light watch that is at rest with respect to system B only ticked about 6.5 times. Therefore, observer B measures a length that is shorter than the measurement of observer A. We therefore conclude that the length of a moving object is contracted. We can also understand why observer B measures a shorter length. For that, we need to look at the measurement that was done in system B one more time from the perspective of system A. As observer B moves along the arrow, her watch slows down from the perspective of A, as we've seen before. Therefore, the time that passes for B is shorter, and observer B measures a length that is contracted compared to system A. By how much is the length as measured in B contracted compared to the length in A, where the arrow is at rest? Well, by the same factor as the time of B slows down compared to A. This is exactly the gamma factor, as we discussed earlier. So we get this formula that shows us how lengths of moving objects are contracted. So we managed to derive two formulas that show how the clock of a moving observer runs more slowly and how the length of a moving object is contracted. In the next video, we will then derive the Lorentz transformation that allows you to go back and forth between the time and spatial coordinates of an event for different observers. After that, we will see how the concept of simultaneity has to be frame dependent as well. And finally, we'll cover the invariant interval. Also, if you want to read more into special relativity or physics in general, I can highly recommend the publicly available lecture notes by David Tong. I put the link in the description.